subclassified.
Yes.
Awesome. Okay, so Navid, thanks for joining us. I enjoyed getting lunch with you at in LA when I was there a couple months ago, and I'm glad you're able to join the group to talk today. I think we'll have at least one ding over the next few minutes as people show up mega late, which is I think traditional for graduate students. But appreciate your time, and yeah, I'll let you take the floor.
Okay, thank you. So should I wait for the Jacob or?
No, don't worry about it. Jacob's smart. He can catch up.
Oh, okay, great. So
All right, they can catch up. Yeah.
So this presentation is this. Okay, sorry. Okay, so this presentation is on neurosymbolic control and verification for signal temporal logic. So while it is applicable on many areas like software engineering or many other things, in this presentation we are mostly focusing on autonomy or these things. So first of all, we want to do control synthesis and also verification for a signal temporal logic specification. So, and for example, if we have a system, we want to make it certain that the system is satisfying a specification, or we want to train a controller for it. That the resulting trace in the system from the system will satisfy a temporal specification. So before starting anything, we need to find a way to encode the temporal specification in mathematical form. So there are many frameworks for doing this. One of them is signal temporal logic. Another is metric temporal logic, spatio-temporal logic. There are linear temporal logic. There are many things that has been proposed in the field, but signal temporal logic is the most inclusive one. So it can cover a lot of specifications in many specifications, and this is the reason that we decide to work with signal temporal logic. But the problem is signal temporal logic is defined on the continuous systems, but our technique is for discrete system. For example, consider this trace that the states are defined on discrete time steps, not on the continuous time steps. So this results to the fact that we want to work on discrete time signal temporal logic, which is DTSTL, which has been also introduced in the field formally, means many papers that are proposed here. So let's first talk about signal temporal logic with an example. So consider we have a drone as our system, and the drone will generate a trace like what you see in the figure, and we want this trace to satisfy a specification, a temporal specification. In this case, the temporal specification says that the drone should visit the green hoop within the next 10 to 15 time steps. Once it visited the green hoop, it should visit the blue hoop within 10 to 15 time steps, and once it visited the blue hoop, it should visit the red hoop within 10 to 15 time steps. So this can be reformed encoded in signal temporal logic as follows, which F here represents the future formula, which means in the future 10 to 15 time steps, there exists a time that the drone is passing through the green hoop. So one nice feature of signal temporal logic is that it comes with a notion that is called robustness, and the robustness tells us how good is a specification satisfied or how bad it is violated. It is quantitative. And this traditional robustness can be computed from a recursive algorithm, which this table is showing that. So for example, assume that we have a formula that says always in the next 15 to 100 time steps, this trace should be always less than 3. So if we consider these two trajectories, the first one is violating that, and the second one is satisfying that. And here the robustness tells us how bad is the violation or how good is the satisfaction of the specification. And in signal temporal logic, it has been proved that in case the robustness is positive, that means the temporal specification is satisfied. So yeah, we have shown this recursive algorithm here, but what we do here in this research is that we reformulate this recursive algorithm in terms of a ReLU neural network, and we talk about the contributions of this in detail in this presentation. So what is the contribution of reformulating in terms of a ReLU neural network? So first of all, we want to talk about this fact, how do we convert this robustness computation for signal temporal logic in terms of a ReLU neural network? For example, consider a very simple specification like this. The state has two components, X and Y, and the specification says globally between 0 and 3, the first component of the state should be positive, or in the future 0 to 1, the second component of the state should be bigger than 3. So this means at the times 0, 1, 2, and 3, the first component should be positive, or for the second component, either at the current time or the next time, it should be bigger than 3. And this should be valid all over the time to satisfy this specification. And this represents the Boolean semantics of this formula, which if phi is true, that means the specification is satisfied, and if phi is false, that means the specification is violated.
And
so in order,
these variables could be things like the height of the quadcopter, how fast it's flying, right? They're like measurable things about the system.
yes, these are predicates that has been defined all over the times, over the trace. And through this tree, we can compute the Boolean semantics of that.
Right. So a predicate is something like it is below 400 feet, and then that is either true or false, depending on the actual height of the thing at each point in time.
Exactly. Okay. So yes, so how that recursive algorithm will be generated, that is by converting these predicates that are Boolean semantics to continuous variables. So in this case, what we do here is that we replace these predicates with the quantitative semantics. So in this quantitative semantics, in case this quantitative semantics is positive, that means the predicate is satisfied. If the quantitative semantics is negative, that means the predicate is violated. For example, one of the predicates says y of 1 is bigger than 3. So its quantitative semantics is y of 1 minus 3. So if y of 1 minus 3 is positive, that means the specification is satisfied. So it is conversion from the Boolean to continuous variables. So when we do this, all we need to do is to replace disjunction with max and conjunction with mean. And in this case, it results to a continuous variable between minus infinity to infinity. And in case this continuous variable is positive, that means the specification is satisfied. And if it is negative, that means the specification is violated. So this is exactly the recursive algorithm I have shown in the previous slide. So what we do here is we want to convert it to a ReLU neural network. So how do we convert it to a ReLU neural network? So we will replace the mean of two variables with this formula, which is a ReLU neural network, and the max with this formula. And we can also extend it for arbitrary number of inputs in logarithmic way like this. So this is the way that we replace this max and means with ReLU neural network. So in case we replace them with ReLU neural network, then we can regenerate reformulate all of this tree in terms of a ReLU neural network, which we call it STL2NN. And here its depth is increasing logarithmically with the complexity of the specification, because the way min and max has been reformulated as ReLU are logarithmic, has logarithmic depths, and tree is also logarithmic. So it generates a ReLU neural network which its depth increases logarithmically with the complexity of the specification, and we call it STL2Net. So now we want to talk about this. What is the contribution of reformulation in terms of ReLU neural network? So what is the problem of the recursive algorithm? Why do we want to do this? And here we want to talk about this. What's the contribution of reformulation in terms of ReLU? So so this figure shows a ReLU neural network that receives a trajectory and returns the robustness. So which each layer we also put all of the ReLU activation functions on the bottom of the layer of activations and put all of our linear activation functions on top. We separate them, and that is because of vectorization and this is a ReLU neural network that we have. So the first contribution of this ReLU neural network is that the problem of verification for signal temporal logic has been something very notorious and very difficult before. But this ReLU neural network converts the problem of signal temporal logic, which was very difficult, to the problem of ReLU neural network reachability analysis, which is something that is very known, and there are many works has been done on that, and this is a very known area of research. So this is the key that converts the problem of verification of signal temporal logic to the problem of neural network reachability analysis, and this is the first contribution of STL2Net. So first of all, in this case, in case the trajectory sigma, the trace sigma is a member of a set. Doing reachability analysis, we can say for all of the trajectories in this set, the value of the robustness is positive, which means satisfaction, verification of a signal temporal logic specification. So first of all, here we show the contribution of this verification on a control system. So we assume, okay, so before that, let's talk about what is the reachability of neural networks. So consider this is a ReLU neural network like the STL2Net that we have, and the inputs are a member of a set. So the problem of neural network reachability analysis computes for an upper bound for the output of the neural network that is guaranteed to contain all of the inputs of the system. So there are many frameworks for doing this reachability analysis: Crown, Polar, Sherlock, ReachSCP, NNV. And between all of them, we are more interested in NNV because NNV is only applicable on ReLU neural networks, and our STL2Net is also ReLU, but it can also provide exact reachability analysis, which is called ExactSR. And also, but ExactSR suffers from efficiency for reachability analysis. In that case, ApproxSR has been suggested. It has a conservatism. It gives us an upper bound on the output set, but its accuracy is high comparing to the other techniques in the field like Crown or Polar. So that was the reason that we have decided to work with NNV, but the drawbacks of NNV is that it is only applicable on ReLU, and we have no problem here because our neural network is ReLU. STL2Net is ReLU. Okay, so let's apply it for a verification and in the area of control. For example, assume that we have a drone with this ODE formula that represents the dynamics of the system, and the set of initial states of the system is like this, and also the controller has been trained for this drone such that this specification is supposed to be satisfied, which means in the future 0 to 25 the drone should visit one of the sets epsilon2 or epsilon1, and always the drone should keep away of the set epsilon3. And this is the specification that the trace should satisfy, and the controller has been trained to satisfy this specification. So here we want to verify that. We want to say for all of the trajectories initiated from this set of initial state, is the specification satisfied or not? So in case you want to say this is satisfied, what is your proof? for doing this, because your controller is a neural network and it is prone to unpredictable behavior. How can you propose a guarantee that there is no trajectory here that will violate this specification, specifically when your controller is a neural network? So this is verification of signal temporal logic. So in this case, what we do here is we compute the reachable sets of the trajectory using the toolbox in the field. So here we have used, I think, reachNN to do reachability over the trajectories. And then once we computed the reachable set of the trajectory, we can introduce it to the STL2NN for reachability analysis. And in case the reachability over STL2NN shows the robustness is positive, that means a proof that the specification is satisfied. So in this case, when you, okay, so what I have done here is that I have partition the set of initial states into 1000 subpartition to make the reachability easier, and I have done this reachability analysis in parallel between all of these 1000 subpartitions, and this value in the x-axis between 0 to 1000 shows the number of partition over the set of initial state. So when you apply reachability analysis on that, so you will see the left bound of the robustness range from the left bound of the robustness range from this reachability analysis over STL2NN is always positive for all of these subpartitions, which means we have successfully verified our specification. And so the runtime for computing the reach tube of the trajectories with reachNN, that is a very known toolbox in the field, is something like this, at most 4 seconds for the partitions. And the runtime for reachability over STL2NN is also at most 7 seconds, which means this verification has been done efficiently. So, and yes, this is the application of verification for a contour synthesis, which was a sound verification. A sound verification means you can only verify, you cannot reject the specification because you have conservatism. For example, when we are computing these left bounds over the robustness values, this is a lower bound on the left bound, which makes it certain that the specification is satisfied if that is positive. But in case that is negative, we cannot say the specification is not satisfied because there is a conservatism in computing this range. So,
Navid, can I just interrupt and point out for people who arrive late that the robustness is a metric that measures, in essence, what is the closest that you get to not being safe. And so if the closest you get is still positive, that means you never actually entered the unsafe behavior. Is that essentially correct, Navid?
yes, no, whenever the robustness is positive, that means your specification is satisfied.
Right, exactly. Yeah.
So it can be, the specification can be something like a reachable formula, which you say it doesn't go to an unsafe set, and it can be also something very, very more complex.
Right, right.
Yeah, for example, in this case, it says in the future 0 to 25, it should visit epsilon 2. So how can we prove there is a state at time 25 in these trajectories that is not inside of epsilon 2? So this is what we have proved here. We have proved there is no way to find a state in these trajectories that is before this set epsilon 2 in the area 0 to 25. Yeah, this is what this verification proves. Yeah, but as you see, the figure is completely acceptable as a proof that the trajectories does not go to the unsafe set, because we have done the reachability. We are not proposing the proof for that. But what about the first part of the specification, which says in the future 0 to 25, you should go through epsilon 2. So, but that is not apparent our proof has shown that it won't happen. For sure, between 0 and 25, your states should go through epsilon 2. Yes. Okay. So, yes. And okay. So we can also use this for sound and complete deterministic verification, which means not only you can verify your specification, but also you can reject your specification, which means the robustness range that we compute is accurate. There is no conservatism. There is no over approximation. It is accurate. So this can be done in some specific scenarios. For example, in case the model and controller are both ReLU neural networks, you can use this technique for sound and complete verification. So how can we do this? We can unroll the model and controller over the trajectory, and then we can introduce the states to the STL2NN to compute the robustness value. So whole of this structure from the initial state to the robustness is a ReLU neural network right now. And in case you apply exact star reachability analysis on that, that means you can accurately compute the robustness range. For example, if the set of initial states is inside of I, then you can compute the accurate value of the robustness range. And in case the lower bound, the left bound of this robustness range is positive, that means the specification is satisfied, which something that is also accessible from the sound verification. But what sound and complete verification gives us is the second option. If the robustness, if the left bound is negative, we can reject the formula. So, okay. So in case the controller and model are both ReLU neural network, we can use this technique for sound and complete verification. Not only we can say it is satisfied, but also we can also say it is rejected. So let's talk about the example here. So in this case, the set of initial states are in this set between the initial states are between the points 1 and 1 and 2 and 2, and the trajectories are starting from that set of initial state, and the model and controller are both ReLU neural networks. So we want to do a verification on this formula. In the future 5 to 8, the robot should visit the set P1, and once it has visited the set P1, then in the future 20 to 24, it should visit the set P4. We can also make it more complex by including the set P2. It says in the future 5 to 8, the robot should be in set P8. Once it is in set P1, in the future 5 to 8, it should visit the set P1. Once it is in the set P1, then in the future 6 to 11, it should visit the set P2. Once it is in set P2, then in the future 12 to 16, it should visit the set P4. This is the specification. The other specification is even more complex by including the set P3. So the difference between the third specification and fourth specification is that I have changed the interval of the last future formula in the fourth one to show that it has got rejected. So we wanna verify the first three formula and reject the fourth formula using our technique. So in this case, this shows the verification result, and the model is a ReLU neural network with one hidden layer ReLU neural network with 8 number of activations, and the controller is also a one hidden layer ReLU neural network with 8 number of ReLU activations. And this table shows by increasing the complexity of the formula, the runtime to do the verification is higher, and the number of neurons that we have in our ReLU neural network from initial state to the robustness value, which also includes the STL2NN and whole of the trajectory, will increase. And also this has shown that for the last formula, the robustness range provides a negative left bound, which means we have successfully rejected the specification for 5.4, but the left bound of the robustness range is always positive for all of the other specifications, which has shown that we have verified all of these specifications. So these were the application in control. So it can be also easily applied in software engineering or something like that. But you should find a way to define your trace. So here the trace is coming from a control system, but the trace can come from a program or something like that. And you can apply that on that area as well. Okay, so now we want to talk about the second contribution of STL2NN. The second contribution of STL2NN is vectorization. So we have previously shown this tree to compute the robustness of that simple formula. So that simple formula, that was a simple formula, which gives us this tree. But what if the specification is more complex? The size of this tree explodes. There are many branches and many things involved, and to compute the robustness, you should traverse over all of the branches of this tree, which cannot scale. So what is the contribution of STL2NN here is that it converts this traversal over all of these three branches with multiplication of a weight to a vector, which means instead of traversing through all of the branches here, you will replace this operation with multiplication of a weight to a vector, which is this linear maps that we have here. So this means that in this case, we can use matrix multiplication instead of traversals using something like GPU that is very that has been introduced for this matrix multiplication. We can achieve a noticeable level of efficiency by computing the robustness from STL2NN rather than using that recursive formula. And here I have shown a comparison between another toolbox in the field, which is STLCG, that I think you are aware of that or not, but it is a very famous one in the field. In that toolbox, they will replace this min and max with RNN neural networks, but they do not convert all of the formula, all of the tree in terms of a neural network, which means they are still supposed to traverse over all of the branches of the tree. That doesn't leave any efficiency for this technique. So here we want to compare our technique with STLCG, and we want to compare it on this specification, which says the vehicle should visit goal 1 and then should visit goal 2 in the future. In is the horizon of the specification, and it should also always avoid the unsafe set here. So the first specification, which is called ordered formula, can be written in terms of conjunction between these future formulas as follows. And this is the specification that we have. So what we do here is we increase the value of k, which is the horizon of the formula, from 5 to 100 and compute for the robustness value of this specification over random trajectories. So what we have done here is that we have computed 1000 random trajectories and computed the robustness for every single one of them, and then we averaged that runtimes. And this shows that the runtime for robustness computation for STL2NN is at least 10 times faster than STLCG, and in some cases it is even 70 times faster. So why is it important? That is important in the training. When you want to train a controller for your system, then you want to compute these robustness values thousands of times, or you want to compute a gradient from these robustness values thousands of times. So when you are 70 times faster, that means your training algorithm is 70 times faster. So this is the contribution. So the second contribution of STL2NN is vectorization. It replaces the traversal over all of the branches of the tree with matrix multiplication, which results to this increase in the level of efficiency for robustness computation and also for computing gradient from the robustness value. Okay, so but but in case we want to apply STL2NN on training process, we have another issue. The issue that is that STL2NN is exactly representing the recursive formula that we have shown before. But that recursive formula is known for its inefficiency in training because it doesn't provide a smooth gradients. So when you want to use that for training process, you will the learning curve is not as smooth, and you will always face the local minima. You cannot improve your values or something like this. And it is proposed in the literature to replace that recursive formula with a smooth version of that, which they replace the mean with soft mean and max with soft max to find a smooth version of that. So we should do this as well on the STL2NN. And we compute something that is called LB4TL. And this is very important for LB4TL, which is a smooth version of STL2NN, to be a lower bound on that. Because our ultimate goal in the training process is to make it certain that STL2NN is positive. So this means LB4TL should be a lower bound for that, because when we say LB4TL is positive, then that means STL2NN is positive, because LB4TL is a guaranteed lower bound. So how can we do this compute this guaranteed lower bound? So in case the ReLU is contributing to the mean operation, we replace the ReLU with soft plus, because soft plus is a guaranteed upper bound on the ReLU. And in case this ReLU is contributing to the max operation, we will replace ReLU with swish activation function, because swish is a guaranteed lower bound on that. And then in case we replace max and mean in that tree with swish neural networks and subplus neural networks, then we can compute the LB4TL, which is a lower bound on the STL2NN and is also a smooth and gives us efficiency in the training process. Okay, so this is the schematic of LB4TL. We arrange all of the subplus activation functions on the bottom of the layer, and we put all of the swish activations on the top of it, and we also put all of the linear activation functions on top. So this gives us the opportunity to compute the robustness fully in vectorized form, and it is also smooth. So the result of this is rho tilde, which rho tilde is a lower bound of the value of the robustness and can be also computed from a smooth operation, which gives us opportunity to do a better training algorithm. So here, so we can use this for neurosymbolic training. So what is the neurosymbolic training? The neurosymbolic training says we have a learnable part in our training process, and we have a symbolic part, which that symbolic part is coming from the prior knowledge of the problem and is logic based and is differentiable. And then we can use back propagation on this computation graph to do training for the learnable part. So in our case, which is the application on the control, our learnable part is the trajectory, which has the controller and the model unrolled over the trajectory. And the logic and the symbolic part is LB4TL. LB4TL, which is coming from a prior knowledge of the system and is logic based and is differentiable. So how we train the controller here is that, so for in every iteration of our training algorithm, we sample a mini batch of new initial states from the system, and we also use this initial states for forward computation over this computation graph, which means computing for the trajectory in the presence of noise and uncertainty. And then we do backward from LB4TL to the initial state. And by doing this, we update the parameters of the controller to satisfy the specification, which is the neurosymbolic training algorithm. And so here we want to compare the contribution of LB4TL with STLCG in training with this neurosymbolic algorithm. So the specification is something like this. Again, like what we have proposed before, we have we want to say that the vehicle first visits goal 1 and then visits goal 2, and it should always avoid the unsafe set. And the model of the vehicle is something like this: x dat, y dat, and theta dat are coming from this dynamics, and the controllers are bounded. The velocity of the vehicle is between 0 and 5, and the steering angle is between minus p over 4 to p over 4. And we use this neurosymbolic training algorithm to train a controller, a neural network controller for this system that provides us V and omega, V and gamma to compute, to generate traces from this vehicle that satisfy this specification. So we use that neurosymbolic algorithm, and for the logic-based part, we firstly use STLCG, which is a very famous toolbox in the literature, and in another case, we used LB4TL. So for the logic part of this neurosymbolic training algorithm. So this table shows the results for 5 different initial guesses on the parameters of the neural network controller for training that neural network controller. And the values here shows the runtime of the training algorithm. So this shows if we use LB4TL in our neurosymbolic training algorithm, our runtime to generate controllers that satisfies the specification is at least 10 times faster. So, and this is exactly because of the vectorization that LB4TL proposed. It is an end-to-end vectorized, but STLCG requires us to traverse over all of the branches of the tree, and that's the reason it takes 10 times faster. It is 10 times slower than LB4TL for doing this training process. Yes, so yeah, that was this paper that we have published in IPAC. Yeah, this is the end of my presentation.
Navid, this is super cool. Thank you for sharing.
Well, thank you so much. Thank you.
So we have a variety of backgrounds here. I'm kind of curious to know if Daniel has any questions since he works on pretty related stuff, but maybe a good place to start would just be like scalability. So you showed us you're 100 gajillion times better at training than, the competitor or whatever, but do you have like complexity theoretic results? Like you are, I don't know, n log n and they are n to the 10 million or something? Like, do we have a theoretical understanding of how you scale versus how prior work scaled, or is it just experimental results to show that you scale better?
Oh no, I don't have proof. It is just experimental results. The idea is replacing the tree traversal with matrix
Yeah.
multiplication, and I have shown the contribution with numerical examples.
Right. Is that actually theoretically faster, or is this just an artifact of how like GPUs are designed that they're really good at this?
Uh, GPU, yeah, the contribution of the GPU is this matrix multiplication,
Right.
and this is
Okay.
exactly what we have done here. We have converted the tree traversal with matrix multiplication, which means GPU is now applicable.
Right. Right. Okay.
Yes.
What are you working on next?
Next, oh yeah, I am currently working on generative models and applying that on scenario generation for signal temporal logics.
Oh, okay. So you could like
Yeah,
fuzz
yeah,
controllers and see
yeah.
if it satisfies specs.
Pardon me?
So you could fuzz a controller and see if it satisfies a spec.
Uh, no, no. I am currently working on training generative adversarial networks, which is a
Yeah.
generative model. So what I'm doing is I am training that on a set of satisfying trajectories to generate new trajectories from GANs that satisfy the specification. And this is a way for scenario generation. But what we are working on right on that is to make it more efficient by
I see.
adding more tools on that. No, using generative models for scenario generation has been done before with Sanjit in Berkeley.
Okay.
Sanjit Seshia. It's Cynic. It's called Cynic. This
Hmm.
toolbox is called Cynic. But I'm working on making that more scalable.
So would you use the scenario generator to test something like a controller for a self-driving car? Is that the kind of use case where this would be useful?
That can be no, yes, for falsification and also to in the experiments to see that when you can generate tons of satisfying trajectories, that means you can use that for falsification and something like this for safety analysis.
Cool. Okay. That makes sense.
Yeah. Mhm.
Can you verify a much larger ReLU, like say with 1,000 nodes?
Larger values. Okay, you know, by increasing the complexity of the specification, which means maybe the formula is more complex or the length of the formula is higher, the size of this LB4TL increases a lot.
Mhm.
But the good news is these matrices that we have, the weight matrices, are very, very sparse. And these can be, there for sure there is a threshold on the value, but our experiments shows that yes, it can cover some specifications that are very complex, something that has been also used in real world examples or something like that.
Mhm.
And that's because these matrices are very sparse. Even if the size of these weight matrices in LB4 are very high, but most of these elements in the matrix are zero, and it will
Right.
not it will not occupy a lot of space and memory, and also the multiplication is also fast.
Okay, cool.
Yes, yes.
I think that's all the questions I have. I don't know if anybody else has any to chip in with, but we can end early if not.
One question I have is how did you get interested originally in studying this work? Like, when did you start looking at this? Why did you think there to go in the directions that you have to have the 10x speed up you were talking about?
Oh yes, I over my PhD I was very interested in finding controllers that satisfy complex specifications, but the existing tools was lacking scalability because of these things that I have talked about. And also, there were also no framework in the literature for verification of STL. So I came up with the idea that converting that to a neural network like this can solve all of these problems. And that was why I worked on this to get my PhD degree.
I did have one question that you showed a slide like halfway through where there were three results that were verified and one that was you found a counterexample. But I thought that with the kind of overestimating, you could only verify but not disprove.
Yes, yes, yeah, that was the sound. That was the sound verification. But in some specific scenarios, we can also do sound and complete.
Oh, really? Okay.
And yeah, so in case that the model and controller are both ReLU neural network, then you can unroll the model and controller over all
It's,
of the trajectory, and then it gives you a very big ReLU neural network, and then you can
right.
apply NLP for reachability on that. This is sound and complete.
That makes sense. Okay.
But it is for very, very specific conditions that model and controller are both ReLU.
Cool. Well, Naveed, this was wonderful. Thank you so much for talking to us.
Thank
Just to confirm, one, is it okay with you if we put the talk online for people who couldn't make it so they can watch afterward?
Yes, 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 yes. Put it
Okay.
online.
And two, you're going off to a postdoc, you said at Vanderbilt, correct?
Yes,
Okay.
yes.
So if people have questions about your work or want to contact you, if, sometimes undergraduates watch these talks and, if an undergraduate's interested in looking for research positions or whatever, research opportunities, should they email your new Vanderbilt email? What's the best way to get in touch with you?
Oh, let's talk. Let's meet my USC email first, and
Okay.
then yes.
Okay. And they can find that on your webpage, right?
Yes. I always check that.
Okay. Okay. Sounds great. All right. Thank you so much, Navid. Really appreciate that you took time out on a Saturday to talk to us, and I hope you have a wonderful weekend. And congrats on the postdoc.
Thank you so much. Thank you so much.
Okay.
Yes.
Bye.
Bye.